Hi, in this presentation we'll be taking a look at a low-cost UAV system for missile defense. Hi, I'm Trent Pancook and I'll be covering Section 1, Establish the Need. Many adversaries have adopted the doctrine of quantity over quality. As such, they focused on swarms and salvos, which pose a difficult threat to counter due to the sheer number of incoming targets, all of which must be successfully neutralized. In the cases of swarms and salvos, not every vehicle is intended to reach its target. The objective is to provide enough decoy vehicles that some will be guaranteed to strike their target successfully. In these cases, cheap and low-quality UAVs and missiles can easily overwhelm existing defense and interceptor capabilities. As such, our interceptor system, which we plan to develop, must be comparably cheap to our threat systems. It must also be capable of intercepting a swarm or salvo of incoming UAVs or missiles, and it must meet the necessary criteria to neutralize threats well in advance of their arrival at intended impact zones.
Hi, I'm Caitlin. Now that we've discussed the big picture and context, we'll be moving on to project stakeholders and industry competitors. For everyday civilians like you and I, our hard earned taxpayer dollars go to fund these missile defense projects, so affordability and availability during high volume attacks is essential. These intercept systems reduce the risk of loss of life and property during aerial attacks, but require a sufficient number of interceptors and short manufacturing timelines to maximize availability. Our second stakeholder, the defense manufacturers, are looking for a design that's scalable for production, with clear requirements and sustainment pathways for long-term support. Our third stakeholder, the mission partners, need to be able to share data and synchronized alerting across organizations. The equipment must be interoperable with their existing command and control, radar, and early warning networks. This is crucial for a layered defense strategy. Military users and maintainers need the system to be easy to use during large-scale attacks, reliable and integratable with their mission planning. Development of a low-cost interceptor could also open the door to international mutual defense contracts, leading to increased U.S. partnerships with other countries. But these stakeholders also need a design that is exportable and transportable to its final destination, as well as interoperable with their existing equipment. So, let's look at some current designs. So how is missile defense currently being done? For low-cost, short-range missiles, four competitors lead the field. The Iron Dome system, developed by Rafael, is probably the best known from current news reports, and performs intercepts using solid rocket motor-propelled missiles and an explosive warhead. They are integrated with radar systems for trajectory calculations. Raytheon Coyote is designed primarily for the counter-UAS mission, but it's also capable of high-speed interception. The Block II UAV pictured here is propelled by a combination of a rocket motor and a turbine engine, and is equipped with an explosive warhead. Unlike some of the other competitors, Coyote is also capable of flight beyond visual line of sight. Anduril's projects, Anvil and Roadrunner, are distinguished by their integration with Lattice, Anduril's AI integrated swarm command and control system with human-in-the-loop for target confirmation. Anvil is designed to intercept small UAVs by ramming into them with its reinforced structure, and uses a combination of computer vision and other sensors for tracking and navigation. Roadrunner is also designed for the counter-UAS mission, with twin turbojets and a variety of sensors. The downside to all four of these systems, though, is their cost, ranging from about $40,000 for an Anvil interceptor to $100,000 or more for variants of Coyote and Roadrunner. Coyote, Anvil, and Roadrunner are reusable, though, depending on the mission executed and whether or not an explosive payload was required. All of these systems require pre-positioning and planning prior to their deployment in the field. Going a little deeper into each of our competitors' missile defense strategy, Iron Dome's effective radius ranges from about 5 to 70 kilometers with Tamir interceptors, and is most effective as part of a layered defense strategy. Due to the limited number of interceptors available, the launchers are integrated with radar systems to selectively intercept only incoming missiles on trajectory to hit critical infrastructure. The system is highly effective, boasting an intercept success rate of greater than 90%, but it's also costly, ranging from $50,000 to $100,000 per interceptor. The payload is a fragmenting explosive, weighing about 11 kilograms. The Coyote system, developed by Raytheon, can either be array-launched or launched from a sonobuoy canister, depending on the variant. Block 1 Coyote, shown below, can be equipped with a variety of sensors, including weather observation for NASA, communications relays, or explosive payloads for the counter-UAS missions. It is designed with deployable wings and can loiter for an extended period of time. However, it is limited by weather conditions and only operable in light rain and moderate winds. The Block 1 Coyote carries a payload weighing about 2 kilograms. Payload capacity of Blocks 2 and 3 Coyote are not publicly available. Anduril's integration with Lattice enables a layered defense strategy leveraging multiple types of interceptors to counter a variety of threats. Both Anvil and Roadrunner are launched from boxes, which can be integrated into urban environments and provide monitoring of UAV health and status. Anvil is a fast, lightweight interceptor, achieving speeds up to 200 miles per hour at a cost of about $40,000. However, it is limited in range and endurance. Only the Anvil M variant carries an explosive payload, estimated at less than a kilogram. Roadrunner is designed for larger counter-UAS missions. Its top speed is estimated to be about 450 miles per hour, with an endurance between 30 and 60 minutes. Cost is the limiting factor for Roadrunner interceptors, from about $100,000 to $500,000. Payload data is not published by Anduril, but estimated to be between 10 and 20 kilograms. Each of these four interceptors discussed has unique strengths and weaknesses, and a slightly different take on the trade-off between cost and performance.
Thanks, Caitlin and Trent, for establishing the needs. I'm Lily, and I'll be covering problem definition. The goal to solve this problem is through designing a low-cost drone which can defend against incoming salvos. This will be achieved by completing 7 objectives, with themes of maximizing coverage of the interceptor while minimizing the cost and time to manufacture. Through a concept of operations, or ConOps, the proposed mission is visualized. Initially, infrastructure will exist like hangars, runways, and local ground stations. There, the system will be ready when the possible detection of an incoming threat is received by existing missile defense system satellites. Once the signal is assessed, it is determined to be a threat. The request to launch the interceptor will be sent to the local ground station. That's when last-minute preparations like opening the hangar doors and activating the interceptors is triggered before launch. While in flight, the drones receive updates from the local ground station. The swarm of interceptors will engage the salvos as necessary, and remaining interceptors will return to base or RTB. While awaiting the next mission, maintenance can occur. All of these mission stages correspond to some functional need of the system. To complete a Defeat the Threat Salvos mission, it must be able to be launched quickly, detect and track the missiles, fly, navigate, receive commands, destroy, and communicate back to the ground system. However, each of these functions are more complex than that. Like the function of flying can be examined as needed to propel itself, control its aerodynamic features, and generate lift. The mission stages can be simplified from 10 to 5, consisting of pre-launch, launch, in-flight, defeat, and reset. This flow block diagram combines the mission objectives with the needed functions to better understand the problem. With such an in-depth understanding of the needs, the system can begin to be defined. This is completed by a house of quality with 11 different rooms, starting with the requirements from the customer. These were explicitly listed as items such as being low cost, quick to manufacture, and actually intercepting. However, through further understanding the customer's perspective, unknown customer needs like interception of multiple types and all-weather operations are identified. Engineers can translate their customer requirements into measurable characteristics with target values like having a large range of 250 miles, carrying up to 20 pounds of payloads, or having a thrust-to-weight ratio of greater than 0.5. These ensure the proposed solution is actually meeting customer needs. As shown in room 3. It's critical that engineering requirements are actually capturing the voice of the customer, so areas of strong relationships like many requirements capturing the need of reduced manufacturing time are identified. The remaining rooms show the correlations among the functional requirements, the ratings of customer needs, the importance of engineering characteristics, and assessing existing products, and a technical assessment of products against our solution.
In this section, we identify what matters most for choosing the right interceptor configuration. Our guiding idea is simple. The propulsion choice and the airframe choice determine whether the system can actually intercept missiles fast enough, high enough, and cheaply enough to scale. We start with the major performance metrics from the requirements. We care about time to intercept because the vehicle must reach incoming missile before they hit defended assets. Weight and power Draw matter because this is a low-cost interceptor. Every subsystem must stay compact and efficient. Cost and complexity directly connect to manufacturing ability, one of the customer's highest rated needs. And thrust, maneuverability, fuel consumption, and altitude performance all determine whether the interceptor can actually reach and destroy high-speed threats. To analyze this systematically, we then break the system into the major subsystem: propulsion, instrumentation, payload, power, and structure, because each contributes differently to altitude, speed, and responsiveness. The instrumentation block becomes especially important since navigation, tracking, communication, and guidance sit at the core of missile interception. Using the subsystem level requirements and the decomposition in the slides, we map everything back into high-level system needs, including missile intercept performance, high-altitude flight, and high-speed travel. This set of metrics forms the basis for the trade study. They tell us what matters most for the stakeholder needs and system ConOps when we compare propulsion and airframe combinations. And these are demonstrations in details. Once the performance metrics are defined, we build the full set of feasible system configuration using these metrics. This metrics combines propulsion choices with airframe types to produce all viable interceptor options. For airframes, we consider fixed wings, helicopters, rotorcraft designs. Fixed wing designs offer speed and altitude efficiency. Helicopters and rotorcrafts provide maneuverability and vertical takeoff. But they generally sacrifice speed and range. Two metrics are ranked highly for missile interception. For propulsion, we evaluate 5 families: turbo alternators, turbofans, turboprops, ramjet or scrimjet systems. Turbo alternators give high power to weight ratios and low cost. Turbofans offers very high threat and altitude capability, but at higher cost and complexity. Turboprops provides fuel efficiency at lower speed, making them attractive before an intercept. Ramjets and scrimjets provide extreme speed but comes with major development risk, material demands, and cost uncertainty. By combining these propulsion types with the airframe categories in the metrics, we generate the full design space for the tree study. These alternatives will then be directly applied into the evaluation stage of our projects when we score them using the key metrics previously defined in Section 3. This allows us to transition cleaning into the evaluation of all these different alternatives in the next section and ultimately justify for you why we select our top choices.
Hi, I'm Trim Pancook, and I'll be covering Section 5, Evaluate Alternatives. In this case, our guiding objective is to determine which UAV configuration, in which the configuration is comprised of both the propulsion system and the airframe, which of these UAV configurations best meets missile intercept mission requirements. This matters because the propulsion airframe choices set overall speed, altitude, maneuverability, payload, and feasibility. We want to understand which propulsion interceptor class provides the best balance of speed, endurance, maneuverability, payload capacity, and cost. As for the scope, the system-level trade combining the propulsion and airframe type is what we will be performing. We'll be integrating the propulsion subsystem analyses and interceptor type analyses. We'll primarily be concerned with the following metrics: speed, or time to intercept. These two metrics are very intimately connected. Maneuverability, altitude performance, particularly concerned in the maximum altitude envelope. Endurance, or loiter time. Range, payload capacity, communication integration, weight and size, power draw and fuel consumption, cost and complexity, and finally, environmental tolerance. Hypothesis-based trade study was completed for 5 alternative configurations in which the following ranked criteria were employed: altitude, cost, payload, range, and speed. The criteria were weighted as follows. Altitude was assigned a weighting factor of 0.1, cost a weight factor of 0.3, payload a weight factor of 0.1, and range and speed both assigned weight factors of 0.25. The results are presented above, with the key off here on the left side. We can see that the number one configuration on our ranking is the turboprop system. Therefore, due to the outcome of this trade study, the turboprop has been selected for this program.
Hi, my name is Noah Cortez, and I'm going to go over the concept that we landed on. So the design that we landed on is a fixed-wing turboprop design. We found that was the best trade-off and the best point for cost and payload capacity. This comes in at about $60K per interceptor, which is much cheaper than the existing missile interceptors on the market right now. This has a 20-pound explosive payload, which is comparable to other interceptors that are targeting this kind of high volume, low cost, low tech missile. It's got a 250-mile range, 500 mile per hour cruise speed, and a 30,000-foot ceiling. We emphasize COTS technology, standard parts, and manufacturing processes to make it easy to produce and maintain, to keep the system's operational downrange as much as possible. You see we have a turboprop, we have the intake in the engine, we got batteries, flight computer, the explosive warhead transceiver, and an IR sensor for tracking the missiles in flight, in addition to receiving telemetry updates from the ground systems and the missile defense network. The operation that we have here is the facility will create a dedicated hangar and short runway for the system. To have an alert posture, there's an elephant walk arrangement for salvo defense with 18 interceptors ready to go at all times. And then there are personnel and equipment on hand in the hangar to prep for the next round of interceptors for the next salvo. Okay, so now I'm going to talk about preparing for the verification and validation of our requirements. We had a good blend of demonstration, analysis, test, and inspection. We leaned most heavily on demonstration to show the performance, show that our system meets the performance requirements. Where possible, we're planning on doing some live fire testing with some real missile systems to prove that it does work as we say that it works. These are just all of the verification testing methods that we. So here's the risk matrix for our design. With the missile defense mission, failure has a very, very high impact because all but certainly you're going to have loss of life depending on the accuracy of the adversary missiles. So we went ahead and mitigated a bunch of risks just baked into the design directly, but there are three that I want to focus on that we can see in the yellow and the red. That's 4, 7, and 8. So risk number 4 is that competing programs remove support for the program. The way that we're going to address that is the rapidly achieve program milestones to reduce the amount of time for the program to be killed. If we can move quickly, then we can get through our program faster than somebody can realize what's going on and try and kill it, and we can field our systems quickly. Number 7 is that the adversaries will send mixed salvos of high-tech and low-tech missiles. The way that we're mitigating that risk is maintaining that communication link between the interceptors and the ground systems and the existing missile tracking networks to make sure that we have high accuracy and high resolution telemetry data so that the interceptors are talking to one another in the air, and then interfacing with existing missile systems, especially higher end ones like the Patriot missile systems, to make sure that for a mixed salvo, we are defending those appropriately. And then number 8, the dedicated hangar protects the interceptors from the harsh environment so they can maintain a ready posture at all times. All right, so in conclusion, our design is effective. It meets the performance specifications. It especially meets the cost and maintenance and sustainment requirements. And it provides the customers with the capability to defend their facilities against high volume, low cost missile attacks, which is particularly high threat in certain regions of the world, and it does so in a way that's not cost prohibitive and sustainable, to let those facilities or the departments as a whole redirect those funds to the operations that matter. The operations that matter.